In this video, we're going to talk about conductors. Some conductors conduct better or worse than others. Conducting means a material allows for the free flow of electrons. The flow of electrons is just another name for current. Another way to look at this is that some conductors resist current to a greater or lesser extent. We call this resistance. Resistance is measured in the unit of ohms, which is noted by a capital Greek omega. So how will resistance affect current? Let's talk about that in terms of Ohm's law. Raising the resistance actually reduces the current, and raising the voltage actually increases the current. These two things are combined in what we call Ohm's law, which is that I is equal to V over R, where I is the current, V is the voltage, and R is the resistance. As you can see to the right of the equation, A is an ampere, V is a volt, and the capital omega is an ohm. So the unit for Ohm's law is an ampere. Solving Ohm's law for resistance or voltage gives us R is equal to V over I, or V is equal to IR. And again, I'll show that video on Edmodo. Raising resistance reduces current, and raising voltage increases current. However, this relationship is linear in only what we can call ohmic materials. If the relationship is nonlinear, we call that a non-ohmic material. So notice here in the graph, an ohmic material will have a linear relationship between voltage and current, whereas a non-ohmic substance will not have a linear relationship. So let's talk about electrical power. Power is defined as the rate that energy is transferred from an electrical energy in the resistor to thermal energy as the resistor heats up. It is the work per unit time, just like when we talk about mechanical power in later units. That is, it's performed by the charges flowing through the resistor. It is equal to the product of the current through which the current goes through the resistor times the potential difference. So power is equal to IV, or it can also be equal to I squared R, or it can be equal to V squared divided by R. Work is measured in joules and time is measured in seconds. The unit of power is a joule per second. In honor of James Watt, who made critical contributions in developing efficient steam engines, the unit of power is known as a watt, a capital W. We use the same units for electrical power as mechanical power. So when we talk about mechanical power, it'll have the same units. So let's think about this another way. The water at the top has a gravitational potential energy and then also a kinetic energy because it's moving. So in future units, we're going to talk about this in more detail. Gravitational potential energy is due to a height. Kinetic energy is due to motion. As the water falls, it loses potential energy, but it turns the wheel. And as it turns the wheel, that energy from the water is being converted into moving the wheel, which we call work. So when the water falls to the bottom, it's now slower because it's done work. So work is a way of transferring energy. Electric circuits are similar. A charge falls from a high voltage to a low voltage. In the process of falling, energy may be used to light a bulb or run a motor or heat a resistor, etc. And that means that work is being done. So how can we rewrite electrical power by using Ohm's law? Remember, electrical power is P equals IV. Ohm's law is I equals V over R. If we substitute Ohm's law into the power equation by replacing the I, we end up with P equals V squared over R. Another way that you can rewrite this is by substituting in for V, and you end up with P is equal to I squared R. What's important here is not the algebra or actually using these equations. What's important is, do you understand what variables are being used? Power is proportional to the current times the voltage. Okay, so if I increase the current, I increase the power. If I increase the battery size, I increase the power through the circuit. Now, if I increase the resistance and I don't change the current, then I increase the power. If, though, I change the resistance, most likely if I don't change the battery, I'm going to change the current and it's going to decrease. Okay, so you have to be very careful with these, and that's what you have to think about. So let's look at this equation right here. Let me get my marker so you can see it. Okay, look at this equation here. If I keep this constant and I increase R, what happens to I? It decreases, right? Now look at this equation down here. If R goes up, but I goes down, okay, by the same amount in order to keep the voltage the same, I is squared. So I'm squaring something that goes down, and that means the overall power of the circuit is going to decrease. Okay, so those are the type of things I want you to think about when working with these equations. What does it mean if I change one and keep another constant? Okay, if I keep the voltage constant and I increase the resistance, the current has to go down. Okay, if the current goes down but the voltage is the same, the power has to go down. And you can also see that here. If the voltage stays the same but the current goes down, the power also has to go down. Okay, those are the types of things that they're going to ask you on the AP tests. They're not going to ask you to put numbers in these formulas. They're going to say, what happens if we add another resistance to this, or resistor to the circuit? What happens if we take this resistor out of the circuit? Okay, so those are the things I want you to think about. Okay, in the next video, we're going to talk about resistivity and resistance.